we're going to do one of my favorite integrals in the world right now. For the purposes of doing our final integral of the day, we're going to think about a particular example of parametric equations. I'm going to do a particular example where everything works out pretty nicely. X is a function of time. F of t is just t itself. That's nice and simple. Y is a function of time. G of t, that's going to be a little bit more complicated. 1/2 t squared. That's a system of parametric equations. It models the motion of, say, a particle along a curve, a parametric curve. And you can use parametric mode in your calculator to plot this curve. In fact, since x equals t, this curve is along the parabola y equals 1/2 x squared. And since x equals t, that means also the motion along the curve as t increases is from left to right. If I had replaced t with negative t, then x would decrease as you move along the curve. It would be from left to right, or from right to left, I should say. I'm getting mixed up trying to think about my left and your right being the same thing. Okay? This motion is from left to right. I might be interested in, for example, how far does the particle travel along this curve from time 0 when I'm at the origin to time 2, say, when I'm at the point. If you plug in t equals 2, you'll get 2, 2. How far is that? What's the length of that curve? What's the distance traveled? I mean, you could eyeball it. Distance equals question mark. I mean, if you drew a right triangle in here and use the Pythagorean theorem, the straight line between these 2 points would have a length of, what would it be, square root of 8? A little less than 3. So a very rough guess here for this distance is about 3. But I'm sure it's not exactly 3. Could we estimate it more precisely? Yes, you can use integrals. And here's how you do it. You want to figure out the speed. First, what is the speed? Realize it really is in general a function of t. I'll call it speed of t. It's not constant speed motion. In fact, starting from t equals 0 and going up to t equals 2, the particle is going to speed up. It's going to go faster and faster because of the t squared there. Turns out the formula for the speed is the square root of f prime of t squared plus g prime of t squared. And for this example, that is square root of 1 squared plus t squared, right? Differentiate those functions up there. Square root of 1 plus t squared. Square root of something squared plus the variable squared. We're going to integrate this thing. What's our goal? Our goal is to find the distance by integration. Integrating the speed does give you the distance. Right? Remember the distinction. Integrating the velocity gives you the displacement, change in position. Integrating the speed gives you the distance. And that does include, even when your motion is not along a line, whether left, right, or up, down, but along a curve. The integral of the speed is still the distance. In fact, if I want to do something kind of general, I could say the distance as a function of t is the integral of the speed. If I'm using t as the variable and I'm starting time at time 0, I go from 0 to t. Once again, emphasizing FTC part 2 here. I'm going to get an antiderivative of the speed. Use a different letter name for the variable. I like using the Greek version of t called tau. Speed of tau d tau. And for this particular speed, this would be then the integral from 0 to t of square root of 1 plus tau squared d tau. Okay, why am I picking a tau? just because it's the Greek version of t and because I think it's kind of pretty. That's why. Just use some other letter. I could have used a W, I could have used a U, I could have used a Z. It doesn't matter. It's a dummy variable. T is the variable for this function. It is the upper limit of the integral. But to do this integral, I need an antiderivative, right? This integral will be an antiderivative. But if I'm going to find it, it'd be best to try to find an antiderivative if possible. So now let's do the corresponding indefinite integral. And I think I'm going to go back to t instead of tau, because ultimately I want to think of t as actual time. T is the variable for distance and speed. So I'd like to do this integral. Okay, it's a trig substitution. But, well, guess what? This one's much harder than the last one. But it's doable. And it involves, are you ready for this? Doing this integral involves numerous steps, one of which involves my favorite math trick, perhaps ever, in my many, many years doing math. We're going to multiply ultimately by a disguised form of 1 to not change a function, but it's the most weird disguised form of 1 you've ever seen in your life. But it's going to help us. It's going to help us do the integral amazingly. It's astonishing. All right. What trig substitution do we do to start with? Sine? No, not sine. In this case, it turns out to be best to do tangent. Let t equal tangent theta so that theta is inverse tangent of t. That's best. Why? We'll see here in a second. If I let the variable t be tangent of theta, that means dt will be the derivative of tangent, which is secant squared theta d theta. Make those replacements. Replace t with tangent and square it. Replace dt with secant squared theta d theta. Why is this good? It looks worse. Well, there's, you guessed it, another trig identity to use here. Maybe you've forgotten it. Hopefully you remember that cos squared theta plus sine squared theta always equals 1. If I divide everything in that equation by cos squared theta, I get yet another identity. Cos squared theta divided by itself is 1. Sine squared theta divided by cos squared theta is tan squared theta. And 1 divided by cos squared theta is secant squared theta. In other words, this thing under the square root is secant squared theta. I'm taking its square root, so technically I need absolute value signs. Do you need to show the absolute value signs? Well, we are going to get rid of them anyway, so I'd be okay with it if you don't. But you should know that in general, the square root of a number squared is not the number itself, but the absolute value of the number. You should know that. If the number is positive, then it's the number itself. If the number is negative, though, then it's its opposite. But we're going to go ahead and get rid of those absolute value signs. So we ultimately, evidently, have to integrate secant cubed. Assume secant theta is greater than or equal to 0, which will be true if theta is in the first or second quadrant. Okay, what do we do now, though? If this were integrating secant squared, it'd be easy, right? Tangent. It's integrating secant cubed. It is secant squared times secant, and that is helpful. Right? This is secant theta times secant squared theta as the product of two things, one of which is easy to integrate. Integration by parts. Secant squared is easy to integrate, let that be v prime. Secant itself is not so easy to integrate, let that be the other thing, u. So u is going to be secant theta. V prime is going to be secant squared theta. U prime, oh, that's worse, is secant theta tangent theta. V, though, is doable. That's tangent theta. uv minus the integral of v u prime. Here with the variables theta, so I'll write a d theta. Okay. Keep going. Keep trudging along. U times v is secant theta tan theta minus the integral of v times u prime as the product of these two things. Yeah. Secant theta tan squared theta. Don't despair. We are going to be able to do it. If we do what we did the other day and call this, say, I, the unknown integral we want to solve for, and we replace tan squared theta with secant squared theta minus 1, after distributing the secant theta through the parentheses here, I will have another integral involving secant cubed, so maybe I can solve for it algebraically. So I have the integral I want to know is secant theta tan theta minus, careful, the integral of secant cubed theta, which is a minus I, plus the integral of secant theta. Got my d theta in here. Sorry, it's a mess there. That's a d theta there. Feel like we're getting closer. Add I to both sides to cancel on the right and balance on the left, giving us 2i on the left equals all what's left there. Divide both sides by 2. I, the integral that we want, secant cubed theta, after dividing both sides by 2 is 1/2 secant theta tangent theta plus 1/2 the integral of secant theta. This is progress. Still not done, but it's progress. At least it's a lower power of secant now. Where's my favorite trick? Right now. I'm going to rewrite that integral to be the integral of a certain fraction. What disguised form of 1 am I going to multiply secant theta by? You ready? This fraction is going to be secant theta plus tangent theta divided by secant theta plus tangent theta. So that'll be on the bottom, secant theta plus tangent theta. What's on the top? I don't want to forget multiplying that by secant theta. Secant theta times secant theta is secant squared theta. Secant theta times tangent theta is, well, just what I said, secant theta times tangent theta. Why did I do that? Guess what? This integral is now trivial. Do you see it? Do you see why it's trivial? Yes? A few people are nodding yes. If this is W, then all of that is dW. The derivative of secant is secant times tangent. The derivative of tangent is secant squared. We're integrating 1 over W dW. ln of the absolute value of w plus c. It's easy. Wow. So the integral of secant cubed is 1/2 secant theta tangent theta plus, don't forget the 1/2 there, 1/2 ln of the absolute value of secant theta plus tan theta plus c. Celebrate. But wait a minute. Are we done? No, we're not done yet. Because we still got to get things back in terms of t. We're really close, though. T is tangent theta. Theta is inverse tangent of t. Theta is inverse tangent of t. So tan theta is tangent of inverse tangent of t, which is t. That's true actually for all real numbers t, amazingly. There's no restriction on t there. And secant theta is secant of inverse tangent of t. I can use a Pythagorean identity, or I can draw a right triangle to help me draw it, figure it out. Turns out to be square root of 1 plus tan of inverse tangent of t squared, because I'm using the Pythagorean identity. This simplifies to square root of 1 plus t squared. I guess that shouldn't be surprising because that was the original function we were integrating. So now this all means the final answer for the integral of square root of 1 plus t squared, the very original integral, which is going to give us, help us find the distance traveled, the arc length along the curve, is combine everything here, go up here. It's all this, but secant theta gets replaced by the square root and tangent theta gets replaced by t. So we get 1/2 t square root of 1 plus t squared plus 1/2 ln of square root of 1 plus t squared plus t plus c. You actually don't need absolute value signs around the ln input because for real values of t, square root of 1 minus t squared will be bigger than or equal to t in absolute value, including when t is negative. And so the input to the ln will never be negative. But it doesn't hurt to leave it there. Is this really right? What does Mathematica say? Mathematica's answer looks a little bit different. Start is the same, but there's a minus sign there instead of a plus sign. Log is natural log, remember, in Mathematica, so that's fine. There's also a minus sign here instead of a plus sign. So did we get the wrong answer? I was wondering that in the first section. Did we get the wrong answer? So I tried plotting both Mathematica's answer and our answer. Here's Mathematica's answer. Here's our answer. And astonishingly, they are the exact same function. And I can emphasize that even by like adding, say, plus 0.1 to this one to get a slightly different function like that. They are the exact same function. Somehow, what I wrote by hand here is the same as Mathematica, even though there's a minus sign here in Mathematica, whereas I have a plus sign and there's a minus sign there. It's got to be some sort of properties of logs or something, and some algebra, some tricky algebra that would confirm that those are the same thing. But evidently they are. Kind of surprising. Is this as simple as it could be? Well, pretty much. I mean, you could bring the 1/2 up into the power of the input of the logarithm here and take a square root of this entire thing. Square roots within square roots. but probably best just to leave it like that. Is it the distance traveled along the curve? Only if its value when t is 0 is 0, if you ignore the plus c. That's 0 when t is 0. When t is 0 here, I get 0 there, but I get a 1 there, but ln of 1 is 0. So if I get rid of the c, it is the distance function. And then if I plug in t equals 2, I get the distance traveled. I can even do it in with Mathematica's answer here. I get the distance traveled at t equals 2 should be close to 3. Yeah, 2.96. You can also see the graph gets close to 3. Yeah, when t is 2, the output is close to 3. This is a graph of how far you've gone as a function of time. Notice it's not a straight line. Its derivative is increasing. This graph's concave up. The speed is increasing. This is the distance traveled as a function of t. So lots of pretty wild stuff today. Amazingly, we got out 4 minutes early. Wow. How'd that happen? I don't know. That's like a record amount of stuff in a record amount of time.